Okay, so I'm going to be talking to you all today about the political economy of blockchain governance. And this is work joint with Barton, who's in Australia right now, and David Parks, who's my advisor. I'm a PhD student at Harvard. Okay, so I'm going to start with some counterintuitive forking behavior that that blockchains have suffered or kind of experienced that need to be explained. And then we're going to try to show a theory that explains them. So we've seen that an extreme policy change can attract more adopters than a more moderate policy. That is, Bitcoin was created in 2009 with a block size limit of 1 megabyte, and there were many unsuccessful forks that were attempted to increase that block size limit. And yet the most successful one is in 2017, an 8 megabyte proposal was accepted. Created a successful new fork, that is Bitcoin Cash. A second confusing situation is that an organization may have an incentive to sabotage its own chain. So in 2015, Ethereum implemented a difficulty bomb into its own chain that would render its own currency useless in a few months. And finally, an organization may have an incentive to propose policy changes even if it's costly to do so and it knows that it will fail. And this may explain why policy proposals are very common despite low likelihood of success. Okay, so what are we talking about? What is blockchain governance? Basically, blockchains are pieces of software that people run, and the code has to be updated like any piece of software. And so when that happens, there's a common history, we call theta naught. And then there's a new proposal, theta or theta p, we'll call later, which forks off from the original chain and which creates a fork in the history. And users face a choice of which chain to adopt, that is, actively use. So what is the governance innovation in blockchains? In the politics we all know and love, or bemoan, an agent may vote, but is actually forced to go along with the majority decision. There's no secession that you can do in the real world. Long live the Queen and don't mess with Texas. Blockchain governance seems like the utopian political system where users have maximal control over policy reform. That is, any user can propose any policy reform that they want, right? However, the potential benefits are complicated by network effects where all else equal, a user prefers more user to be on their chain. And entities like cryptocurrency exchanges, which are influential in the success or failure of forks. They can choose to list or delist and choose which fork is the genuine fork. So in this paper, we build a positive, that is, explanatory model and theory of blockchain governance, considering the founding blockchain principles of decentralization and openness and network effects and the influence of exchanges. And we use this model to understand why and when forking occurs and how some of the counterintuitive behavior I explained above can be explained. Okay, so the outline for the rest will be I'll show the model. And basically, we're going to be talking about a single-dimensional policy space, which we can think of as just the debate over block size. So there's a real line, and you can be a 1 megabyter, and I can be a 4 megabyter. And then we'll consider what each individual's utility actually is, considering that they have some particular preference, like 4 megabytes. And then we'll talk about the results, what this model actually shows. We'll show incentives for extremism. We'll show fork outcomes. And we'll show an incentive to sabotage. Incentive to sabotage your own chain, that is. Okay, so the model is big theta will be a one-dimensional policy space, and we'll call that the real line. And the status quo policy we'll call theta naught will be at 0, just for the sake of the model. And there's a unit mass of agents who are distributed according to some distribution function f, and that is their that distribution is of their personal preference, their optimal policy. 4 megabytes, 8 megabytes, 10 megabytes, 100 megabytes, whatever. And initially, there's a chain operating with the status quo policy theta naught, and which has the entire unit mass of users. And now users have preferences over a new policy, which we'll call theta p, and the mass of other users, that is Q, which we'll call QP, who adopt. Okay, so here's the benchmark model. So an agent P with proposal power makes a policy proposal theta P to replace the status quo theta naught. Okay, so we can look on this is the kind of policy space on the real line on the x-axis. So theta naught is the current kind of status quo. Theta P is the proposed policy. And theta I is kind of the optimal policy for user I. And this curve is the distribution of these optimal preferences over all the users. And we're going to say that, that an agent I's utility from this pair, theta P, QP, where theta P is the proposed policy, and QP is the proportion of users who will adopt that new policy. So a user has a preference, a utility, from that pair, from the policy and the amount of users that actually adopt that policy. And that utility is going to have a term which is like a distance term from their optimal parameter, theta I, right? So that's the distance between theta P and theta I in either direction. And then it's going to have a network effect term, where actually users want more people to join their team. And so as QP grows, kind of this G function is going to grow. It's an increasing function with QP. And then alpha is like a personal preference, you could say, or maybe a network preference for how much users actually value the network. Kind of, you can have super individualistic networks or kind of networks that really care about the community. So alpha is greater than 0 is a measure of network importance, and GQ is continuous and increasing. Okay. So now let QP be, as I mentioned, in equilibrium, the fraction of the whole that will adopt theta P, giving users common knowledge of that distribution over theta I. And then the adoption kind of condition will be that agent I adopts the policy theta P over theta naught if and only if kind of the utility from theta P, considering the amount of people who will adopt P, and the utility from the status quo, given that QP will leave the status quo, right? So you want the left-hand side to be bigger. That's the case for adoption. So now if we consider the marginal adopter, that's a little cut off here, but if you consider theta M, which is here, to be the marginal adopter, that is those to the, this is theta P, right? So those to the right of theta M are going to adopt, and those to the left of theta M are not going to adopt. And now we consider where theta M should be given this network effect. Okay, so if the network, if more than half of the network, for example, is going to actually go to the proposal, then we would imagine theta M would be on the left side. This is theta P over 2. So if more than half of the network is, so if more than half the network joins, right, at QP greater than 1/2, then theta M will be less than theta over 2 because kind of more people will be pulled in, just as a matter of the network effect. Okay, and now let's think about, is there an extent, so I'll describe if there's an incentive for extremism in this new model. In standard models of political economy, so our co-author, David and I are computer scientists, but our co-author Barton is a political economist, and in standard models of political economy without network effects, more extreme policies, as you might expect, kind of intuitively, more extreme policies should attract lower support, right? So if you think about the marginal adopter here being theta P over 2, kind of the proposal is theta P, the status quo is 0, the marginal adopter is going to be theta P over 2, and the massive adoption is going to be kind of the sum of the area under this curve to the right of theta P over 2, right? As theta P grows larger, theta P over 2 also grows larger. And so that curve, kind of no matter what the distribution is of user preferences, the size under the curve is going to be reducing, right? So and here we see kind of the adoption amount. So as P gets more extreme, moves to the right, adoption decreases, okay? That seems intuitive. And remarkably, in the case of blockchain, the opposite can occur. When you have these it's not really the case of blockchain, but when you have network effects, the opposite can occur. More extreme policies can attract more adopters. So this is actually what our adoption curve is going to look like. Going from 0, which is the status quo, as you move right, we're going to see 0 adoption for some time. Then there will be some critical point, theta bar, okay, where kind of the first user is willing to join. And then, as you grow, as you make theta p more extreme, more people will join. This is kind of the unusual thing. As you get more extreme, more people join, up to some maximum, theta star. And then, as you keep going even more extreme, then the amount of adoption will reduce. Okay, how do we explain such a thing? So now let's think about, so first, as you're moving as you're pretty close to 0, and you're moving the proposal to the right, there's all these people kind of along the distribution who actually prefer that policy to the status quo, right? Because they're to the right. So the policy proposal will be here, and they're to the right, so it's closer to them than 0 is. But actually, the reason they will not adopt is that not enough people are going to join them. And finally, you get to the point, theta bar, which is going to be the point of indifference for the most extreme user. So now you think about the most extreme possible, the person who thinks there should be no limit to block size, whatever, 10 gigabytes blocks. Okay? That person is out here, theta E. That's the ideal. And you can see that their utility is maximized. Their utility is maximized at theta E. So now we can think about what is their utility what is their utility when no one joins them in the status quo? That utility is going to be minus theta E squared, right? Just because of because the network term will be 0. And now, if everyone has joined them, as in the status quo, everyone is on the status quo, their utility is going to be minus theta E squared plus alpha. Alpha is the network importance term. And now let's think about the policy that's further to the right of status quo that is just going to make them indifferent between being with everyone else on the status quo or being alone on this policy. Okay, and this is for the most extreme agent. So that's actually going to be our theta bar. And then as we keep increasing the theta, as we keep increasing the extremity of the proposal, support is actually going to increase because you're satisfying more and more people's condition here because this curve will move to the left. Because when this curve moves to the left, this point moves to the right. And furthermore, they'll be backed up by the network effect of other people joining. Uh-oh. Okay, we're back. Okay, so that's why this curve is increasing for some time. So 0 for some time, then increasing unusually as you get more extreme, and then decreasing. Decreasing because eventually you get so extreme that no one's going to join you anyway. They prefer the status quo. Okay, so this theory might help explain why a more extreme policy change may attract more support than a more moderate change. So in the Bitcoin block size fork debate, 2 megabytes kind of did not succeed in making a good kind of stable chain. And just, can be a bit debatable, but 8 megabytes did. And the implication is that extreme agents can drive adoption, and they can initiate a kind of herding around them, and that network externalities lead to an incentive for extremism. So now let's think about, in this graph, we consider that any set of users can create a fork by themselves. But actually, kind of, we see in real life that's not the case. Basically, if you create a fork that's too small, then no one, the kind of exchanges won't list it, no one will care, et cetera. So in reality, there is some kind of Q-min, like a minimum number of people that have to care and join you so that you actually have a chance of being a feasible new fork. And when you get that, when you introduce that kind of minimum parameter, you get the three kind of forks that we see. Basically, if the proposal fails to meet this minimum bar, then we call this a null fork. Basically, nothing happens, everyone sticks with the status quo. If the proposal succeeds, in having a mass of adopters between this kind of minimum bar, Q-min, and 1 minus the min, then you get a contentious fork. Okay, and this is like ETH and ETH Classic, or Bitcoin and Bitcoin Cash, where both chains are viable. And then sometimes the proposal succeeds with QPs greater than 1 minus Q minimum, so that's kind of the status quo no longer is sufficient to meet the threshold. And in that case, we call this a non-contentious fork. Kind of everyone agrees that we should fork to the new thing. And this is what we see with Ethereum hard forks. Right? Ethereum has hard forked several times with no problem, with no kind of contingency left behind. And kind of some insights from our model are that as you increase this network importance parameter, alpha, contentious forks become non-contentious forks. And that kind of makes sense intuitively because if people care more about network, then they're less likely to go unless everyone else is going. And similarly, as you increase this kind of minimum Q bar that exchanges set, Q min, that exchanges set, similarly, contentious forks become non-contentious forks. And more great insights await you at the paper site, which you can find on the program. So now I'm going to go over kind of an interesting special case, which I think our model helps explain, which is why Ethereum implemented this difficulty bomb, right? So Ethereum's currently proof of work, but there's been a push for a long time towards proof of stake. In 2015, the EF committed to implementing the policy by programming a difficulty bomb. They said, if we're not done in 3 months, our whole chain is going to be dead, so we better get it done. Of course, we're in 2020, and there's been no such change. And the difficulty bomb has been kind of pushed back and back. Each new update has delayed the bomb and also implemented other changes. So how has this actually been useful for them? The difficulty bomb, what actually it does, it makes the status quo policy completely unattractive to anyone because the chain is going to die in a few months. So the chain has to fork at some point in the next few months. And this shifts user preference away from the status quo and towards new policies. That is, it generates consensus for change. That's how they can get these non-contentious hard forks. And this allows the Ethereum Foundation to implement non-contentious forks more easily without losing users. So in summary, we created a model to help explain the different kind of forks. Failed forks, contentious forks, and non-contentious forks. And we also explain how an extreme policy change can attract more adopters than a more moderate policy change, which is counterintuitive, and how an organization may have an incentive to sabotage its own chain. That's all. Thank you.
Thank you, Dan. If people want to line up for questions. And our first question is from Wasim.
Hey, Dan. Forking, great talk. I also love forks. So I have a question for you. So you're building these models, and then you're using these models to try and explain and rationalize things that we see in the wild that perhaps don't tally with our pre-existing notion of how things should be. Usually the next step in kind of the building of the model is to then apply this to do some predictive, to make some predictive insights. So are there any kind of new types of forking phenomena that you might anticipate based on the work that you've done here?
I guess the closest thing is this, is these kind of insights where these are the kind of outcomes that our model gives that don't necessarily explain phenomena we see yet, But kind of as things might change, so if we see that a network that used to have kind of a high network preference, the community was very important, and then somehow community became less important, then you would get kind of the opposite of this effect. So kind of non-contentious forks that were able to occur before would result in kind of a more splintering effect. So that's the closest that I'll say.
Thank you for that. So thank you. I'm just sort of missing something, I think. You assume network effects, I agree, but network effects induce power law distributions, and you started with a normal distribution, and the best example of that is SSRN. You look at the popularity of papers, it's a classic power law. So are you trying to prove a power law starting from a normal distribution, or why did you just start with the power law?
Yeah, this is, I think, agnostic of distribution. So any distribution is fine.
But if you're going to assume, right, but it is a power law. You're basically saying there are network effects, so of course there's a power law. And so there's going to be a sweet spot. Goldilocks is too hot or too cold, or you have the perfect one, a proposal for forking or whatever. So of course there's power law effects because of, well, you'll see a power law distribution. And I can certainly imagine that comes because if it's not radical enough, it's not worth the pain and the risk. And if it's, as you point out, too radical, no one will do it. So there is enough that, yeah, it's worth it to do 8 gigabytes or whatever the problem is, and it's not too little, and it makes sense. But again, I think you might want to start with power laws and just falls right out.
Sounds good. Sorry, David, my advisor, David here, has a point.
Really quickly, the distribution is on the preference of users. It's not on the size of the network about. Your power laws are about size, not about the preference distribution.
No, the power law is on the size of people who like the, whatever your question is.
That's endogenized to the adoption. The normal plot he showed you is the underlying. We can take it offline.
Yeah, please, please.
Okay, yes, hi.
I really like that. I have a very minor point about the contentious forks. Wouldn't it make sense when modeling the preferences to explain the free outcomes and the preferences in terms of the value of each asset? Because you're talking about hard forks, right? So I end up with both assets. And so when you model my preferences, I should have an expected value for the kind of original and the forked product. Yeah. And because both are subject to network effects, there is a kind of an equilibrium outcome for these preferences that I think is perhaps better explained by the value of the forked product than just the general network effect factor.
I totally take that. There's a great question of when there's a fork, what does it mean to use a particular branch of the fork? Because in fact, you do get both sides of the fork. But actually what we see often is that people choose, and they sell kind of their stake in one of those, and they choose the kind of one or the other. So it means realizing like the immediate value, right?
Yeah, but I mean, so you would expect that your decision is based on the expected utility you get from whatever you do with those two assets, right? So do you think that the fact that there is a fork product reduces the value of the original chain by more than what you can sell the other asset for or not? And that should be your decision criteria. Whatever your ideological commitment to one of the two branches, you should worry about this trade-off, right?
I think basically people's preferences, we assume that people's preferences are more long-term than just this kind of this immediate, like, we assume that people kind of cash out of one and realize the full, because they're hoping for some kind of long-term actual, not only just currency value of the other. Yeah, please. Neha, yeah.
Just really quick on that topic. I think you have to think about future users and which side of the fork actually retains the name and the listing on exchanges, things like that. There is kind of a winner-take-all with a lot of forks, where one becomes the primary coin, and even if you're holding some other, you have to think about future users buying into that, and that's it.
Thanks, Neha.
So just a couple points and a question. One point is that there originally wasn't an explicit block size limit in Bitcoin, although there was an unintentional 32 megabyte limit due to the way the code was constructed. And then it was until later that Satoshi put in a 1 megabyte block size limit as a temporary, even though blocks were much, much smaller than that. But they realized that there could be a potential spam vector there, or it could break the network if people started making 32 megabyte blocks.
Right.
Also, there was always an assumption with a fork that within Bitcoin that there wouldn't be enough hashing power on a minority chain. So essentially, blocks would be hours apart, and it would be abandoned. So what was interesting was even though BCH has like less than 5% of the hash power of BTC, they not only hard forked to change the block size, but they hard forked to also change the difficulty adjustment algorithm, so that the difficulty could adjust down, so that it could continue.
I'm a little confused at that. The difficulty adjustment algorithm, regardless of if you switch chains, I think the difficulty adjustment algorithm will shift so that it won't be hours apart, right?
Well, eventually, but if you have a more than 95% drop in hash power, then the blocks will be instead of 10 minutes apart, will be 200 minutes apart.
Yeah, for like a few days or whatever.
And it wouldn't be 2 weeks to be the adjustment. It would be like 40 weeks.
We've got to get to our last speaker, so maybe we continue this after during the break.
I just want to, just another question, which did you look at like the, like saying like the Overton window, or like how people on social media are promoting their ideas of the forks? In terms
Have
of
not,
how they might affect it?
but definitely great idea for future research, kind of thinking about kind of a more empirical side of how people are thinking about what ideas are acceptable and so on, as you're saying.
All right, thank you, Dan. And now